Okay, first, does anyone have any questions about the homework that was due today? Yes. 1 and 3. Okay, so question 1 first. What's your question?
Just the general concepts of the draining and charging capacitor with the graphs.
Okay, so I can go through 1, and then 3 is pretty much the same thing, or I can go through 3 and then 1 is pretty much the same thing. It's the same process. So do you have a preference? Because I don't want to do like the entire homework. 3? All right, which one? 3B? All right. So the process is going to be the same for everything, so we'll go through this one. All right, so all right, 100 micro. I don't have one. Okay, so to the camera. Does anybody have a stapler that he can borrow? Alright, so let's look at this. Alright, so we're going to be plotting these signals, right? So over here I'll draw like a plot. Time, and then I've got voltage. We'll call this V in, Vx, V out. Okay, so first, the first thing I would do is I would determine what's V in doing, because V in is probably the easiest to determine because it's just based on the pulse source, right? So based on the pulse source, it basically goes 0 to 10 volts, right, at 100 microseconds, and then it stays on for 600 microseconds. Okay, so if I go back here and I wanted to draw that, let's call this like 100 micro. This will be 700 micro. And then that's all that we really need for now. So V in basically starts at 0, right? And then at 100 micro, it's going to jump up to 10 volts. It's going to stay on for 600 micro, and then it's going to drop back down, right? You good with that? Everybody good with that? Okay, good. 10 volts. Okay, so now we want to know what's happening with the other signals. Let me draw those same timestamps. Okay, so like I said, I personally think the best way to solve these is using the KVL method. You don't have to do that. Is that what you tried to do? Like what I did last time in class? Yeah, but like to determine where these voltages are jumping, and did you try to use KVL? Okay, so that's what I'm going to do. So basically, immediately after the switch jumps from 0 to 10, we know my capacitor can't charge any. It can't charge instantaneously. So I'm going to basically draw an equivalent circuit where instead of a pulse, this is just 10 volts, right? And I know that initially I don't have any voltage across my capacitor, right? It's discharged. Okay? So, and then this is Vx, and this is Vo. Alright, so I'm going to draw current, and I'm going to do KVL, okay? So if I do KVL, all I care about is the voltage drops across each component in the circuit. So when I start, I'm going to start at the bottom of the battery, just like I would for any KVL, okay? And I'm going to go up across the battery, and when I go from, the bottom to the top of the battery, I go up by 10 volts, so I'm going to write 10 volts. Now the capacitor has no voltage across it, so I could write plus 0 or minus 0. That's not going to really affect anything, right? Now I go minus I times 4K minus I times 6K equals 0, okay? So if I solve this, I get 10 volts equals I times 10K, or I equals 1 milliamp, all right? And so basically, I know now that this I, at that moment when the battery, at this moment in time, 100 microseconds, when the pulse source reaches 10 volts, I have 1 milliamp flowing in the circuit. Okay, and if I have 1 milliamp flowing through this 6K, what is V out? Exactly. So V out is going to jump up to 6 volts. Okay? And if I have 1 milliamp flowing through this 4K, what's my drop across the 4K? 4 volts, exactly. So then my Vx is 6 plus 4, or 10 volts. Okay? So Vx also jumps up to 10 volts. Which makes sense because, like I said, the capacitor acts like a short. So if this side of the capacitor is at 10, Vx is also at 10 for that instant. Alright? And now, from here is where the charging equations take over. The charging and discharging equations. You want to do KVL on the edges, but in between you have the charging and discharging equations kind of dominating. Okay, so I had some people come to my office today to talk about this. Basically what we want to do is, here, we'll distinguish between Vx and Vo. We want to look at what is their initial values and what is their final values so that we can determine what to plug into the equation so we can generate this equation, right? We're going to be using the Fife equation. So my capacitor voltage, or sorry, not my capacitor voltage, but whatever voltage I'm interested in is going to be the final value plus the initial minus the final times e to the minus t over tau, right? That's the Fife equation, all right? So that's what we're going to be using. And so basically, I need to determine what's going to be my initial and what's going to be my final for Vx, what's going to be my initial and what's going to be my final for Vo, so that I can determine what the equation is that governs the behavior of that particular node. All right? So Vx initially is 10 volts, right? You agree with that? Okay, so I think what's interesting here is that yeah, because this is the third problem. I basically gave like 3 different scenarios. So what you have to note is Vx is initially going to be 10 volts. And then the question is, what is Vf? Basically, what is that node Vx eventually going to go to? And when I ask that question, I ask to say, what is the voltage going to be at Vx when there's no current flowing in this circuit? Okay? And so if this was just a circuit right here, like if we're just looking at this circuit right here, and you know that there's no current flowing at all, what would Vo and Vx be? Do you know why they would be 0? If there's no current flowing, then there can't be a drop across this 6K and there can't be a drop across this 4K, and they're both connected to ground, right? So the final voltage for Vx is going to be 0 volts. And then Vo, its initial value is 6 volts, right? And its final value, again, is going to be 0 volts because it's going to get pulled to 0 once there's no current flowing in the circuit, okay? So basically, these are going to both discharge at a rate of 5 tau. What's my tau here? 10K times 10 nano. Is that 100 micro? Yeah, so tau is 100 microseconds, which is why I gave like 600 micro, so after basically at like 600 micro they should be mostly discharged. I guess I didn't draw that one great. Okay, so if I wanted to write equations for these, I would just plug this VI and this VF and my tau into this equation. And now I can find actual voltages. So for Vx of t, I would say Vf, which is 0. Bless you. So my Vf is going to be 0. Do you see that? So these are going to go away. So I basically just end up with Vi e to the minus t over tau. So Vi is 10, e to the minus t. Now note, I have to include that initial time that nothing was happening. So I have to subtract 100 microseconds. Because that's basically shifting the curve by 100 microseconds. And then I divide by my tau. So that would be my equation for Vx of t, at least between 100 and 700 microseconds. Okay? So basically 100 micro less than equal to t less than 700 micro. I kind of ran out of room, but you get what I'm saying, right? And then for V out, or VO, I write the equation. Instead of starting at an initial value of 10, it starts at an initial value of 6. So this one's going to be 6e to the minus t minus 100 micro over 100 micro. And that's going to be basically over this same time frame, from 100 microseconds to 700 microseconds. Okay? So now that's basically the first half. We've gotten the rising edge of the input taken care of. Now something else is going to happen at the falling edge of the input. And so I'm probably going to need another piece of paper here. Does anybody have any questions about anything I've done so far? Yes.
On the homework, do you care whether or not we plotted like actual values for our curves, or if we just sketched them?
If you just sketched them, that's fine. But on the quiz, you need to know how to actually plot the points. So.
Okay. I ran out of time for the homework, so
Yeah, that's
now I
fine.
regret plotting actual values. I was sitting there crunching numbers.
Oh, I mean, it's good to do it because it's good practice, but it's not super necessary.
Gotcha. Good to know for the future.
All right, so basically now what I'm going to do is I'm going to look at the falling edge. So let me redraw the circuit. This is still homework 14 3B. And I'm basically looking at the part where it falls from 10 back down to 0. Oh, I've got a cap. Then a resistor, then a resistor. And this is Vin, Vx, Vo, 10 nano. Okay. So now I'm going to do KVL again on the falling edge, right? I said we want to do KVL on the edges, so I'm going to draw an equivalent circuit again. But this time, my battery is 0, right? It went down to 0. So I'm just going to draw this as a wire to ground. I don't need to draw a battery there. It's going to have 0 volts across it. My capacitor now is charged to 10 volts, okay? And I've got 4K, 6K, and ground. And so again, I'm going to do KVL. So if I do KVL, I'll start at this 6K. I'm going to drop minus I times 6K. I drop minus I times 4K. And then when I get to my capacitor, I can just treat my capacitor like any other component. It has 10 volts across it. So I'm going from this node to this node, I'm going up by 10 volts. So I'd write plus 10 volts equals 0. That's my KVL. All right? So if I rearrange, I get 10 volts equals I times 10K, and again I get I equals 1 milliamp. Note that I drew the current flowing the opposite direction this time because the capacitor is discharging, it's not charging. And so what's going to happen now is I need to analyze the same way I did last time, right? I came here and I said, oh, okay, I have I flowing through this 6K, so my V out is going to be 6. I have I flowing through this 4K, so my Vx is going to be 10. I'm going to do that exact same thing over here. Let me switch colors. Okay, so if I have I flowing up through this 6K, I get a drop of 6 volts, right? But I'm dropping from 0 by 6 volts, so this is going to jump down to negative 6. Everybody see that? And then going the other way, I'm going to drop by another 4 volts. So this is going to go down to negative 10. Okay? And so if you notice, this is at 0, this is at negative 10, we maintained that 10 volts across the capacitor because the capacitor's voltage can't change instantaneously. So let me come back here, see if we can, yeah, that's good. So basically what I'm going to have is I'm going to have Vx is going to jump down to negative 10, right? And then my VO is going to jump down to negative 6. Okay? Everybody clear? That's clear with everybody? Yeah.
Could you kind of work these backwards? Like I knew that there was going to be an absence of voltage, so I was going to take what that max voltage we had before and just make it negative, and then work it that way. Basically, I used that to find a negative current, and then like it's essentially the same thing, right?
Hang on, what did you mean by there's going to be an absence of voltage?
Because we talked about, like in class just Monday, we talked about like the reason why it flips to negative is because you have to remain that potential difference. So we know there's a potential difference over that capacitor of 10 volts, but because it's 0 volts, it has to go to negative 10 volts to maintain that difference. So I just like rationalized that that's what was going on, and then found my drops the opposite way.
Yeah, that works. That works because I imagine what you're saying is you knew this was 0, you knew you needed 10 volts across it, so you knew this went to negative 10. In the other case where we described it in class, that was problem 1 on the homework, where you don't know the voltage on either side of the capacitor, so you kind of need to do KVL to decide. But in this case, if you know this is 0 and you know this has to be 10, then yeah, of course this is going to be negative 10, so you don't have to do this. And then from there, if you know that's negative 10 and this is 0, you know you have 10 volts across 10K in series, so you get 1 milliamp. That's what you're saying?
I did KVL with negative 10, so I got negative 1 milliamp, and then just calculated my drop down.
Yeah, that works. Yeah, that works. Okay, so from here, now the last step is to basically redo what we did on the first page, which is determining what my initial and my final values are going to be for the charging and discharging equations. So let's write it up here, I guess. We'll write Vx and VO. Okay, so Vx is initially going to be negative 10, right? We saw that it goes to negative 10. And so then what is Vx's final value going to be? When no current's flowing in the circuit, what is Vx going to go to? Exactly. And so for the out, it's going to initially go to negative 6, and then what is it going to go to when there's no current flowing? Okay, so now we can write the equations for these two, and I don't want to write them all out again, but basically you'll get that this comes up in 500 microseconds, and this also comes up in 500 microseconds. And then once you have all those equations, another thing I wanted to mention. So you know what? Let me write them just because I've been wanting to mention this, and I haven't to a lot of people unless you came to my office. Does everybody remember piecewise equations from algebra? Basically, that's what we're looking at here. We've got 3 segments. We've got a segment where nothing happens. We've got a segment where this node is basically discharging from 10 to 0. And then we've got a segment where it's charging from negative 10 to 0. Okay? So let me write the equations for Vx and Vout here. So in this case, Vx of t is going to be, I'm using Fife, so final plus initial minus final. So my final is 0. My initial is negative 10, so I basically get negative 10 e to the minus t, and this time it's shifted by 700 microseconds. Okay, so I need to subtract out 700 microseconds to account for that shift. Okay, so that's my Vx of t for that last segment. That's for basically 700 microseconds. Wait, hold on. It's basically for t greater than 700 microseconds. Okay, so if I were going to write a piecewise equation for Vx, I've got 3 segments, right? Let me just put them on the screen. Okay, so I'm looking at Vx. So if I wanted to write like a full-blown equation for Vx of t, I would basically say Vx of t, it's 0 for t less than 100 microseconds, right? Nothing's happening to Vx for the first 100 microseconds. Everybody see that? And then I have another segment from 100 microseconds up to 700 microseconds. And then I have another segment where t is greater than or equal to 700 microseconds, right? So Vx of t is 0 over this time span. Over this time span, it's that first equation that I came up with. So I would write 10 e to the minus t minus 100 micro over 100 micro. Okay? So that equation holds true over this time span, from 100 to 700. And then the last equation that I just came up with, which is negative 10 e to the minus t minus 700 micro over 100, that holds true for all the time greater than 700. Does everybody understand this? This is piecewise, algebra equations. And so basically each of these plots could be created, a full-blown function could be created by making a piecewise equation like this. Does this make sense?
Yes.
Does it not make sense to anybody? All right. Any questions about this problem in general before I move on to inductors? Yes.
So I did it by treating it like a short, and then is it okay to do the voltage divider
Yeah.
instead of KVL?
Yeah.
Oh.
Yeah, however you see fit. As long as you know how to generate these equations, because on the quiz I'm going to ask you, to plot specific points. So as long as whatever you did, you're comfortable with generating these equations, that's all that matters, really.
Okay.
All right, let's go on to inductors. I started talking about them last time. No. Okay, yeah, I wanted to come back to that topic. So capacitors, inductors, and resistors all have impedance in AC, so it wouldn't make sense to call all of them impeders. I mean, you can if you want, but they're just components. All right, so as I mentioned last time, an inductor is just a coil of wire. Typically, you'll see its symbol. It looks like this. It basically looks like a coil of wire. Let me just pull it up in Spice real quick so you can see. Many of you may have seen them before. If you hit L on the keyboard, it gives you an inductor. Okay, so this is an inductor in Spice. Its impedance is L, or not its impedance, sorry, its inductance is L. I don't know why. Again, we can't use I because we use I for current, so someone decided to call it L. And inductance is measured in units of henries, H. I don't know who Henry is. I don't know who that is either. Okay, and again, similar to capacitors, right? They're going to be fairly small values. You'll see microhenries, millihenries. You won't generally see henries. Like the way resistors use kiloohms, right? It'll usually be smaller values, micro, milli. Henries? You're going to have to get used to it. I'm sorry. I mean, Farad's a name too. It just doesn't sound so common. Teslas, yeah. I mean, every unit is named after somebody.
But we know who those people are, though. We don't even know who Henry is.
Well, I don't know who Henry is. You guys want to look it up?
Yeah, I kind of need to know who Henry is.
And then there's the unit of conductivity.
Oh yeah, Siemens.
Oh, my God.
They actually came up with a separate name for that because they didn't like it. It's like they'll take ohms and just flip it, and they call it mhos, M-H-O-S, for conductivity. But that's also named after a guy. Physicist Joseph Henry, abbreviated H and named for the American physicist Joseph Henry. 1 Henry is the value of self-inductance in a closed circuit in which 1 volt. Yeah. I don't know.
Dang.
I guess he looks like this. Look, here's all the names. Oh, see the conductance. Here's the Mo's I was talking about. I'm not repeating myself here. I noticed a lot of you put joules when we were trying to find charge across the capacitor. Charge is in coulombs, it's not in joules. Joules is energy, so just make sure you know that distinction. Okay, so back to inductors. What we know about inductors and capacitors are very inversely related. They're very opposite of each other, but a lot of their behavior is similar. Basically, we know that a capacitor acts like an open in a DC circuit, right, when no current's flowing, while an inductor acts like a short in DC circuits. And the reason is that it's literally just a wire. Okay? So in just a typical DC circuit, if I were to draw, like a 5-volt battery, I have a resistor, and then I have an inductor, and nothing interesting is happening here. Let's say 1 millihenry and then 10K. This would just be 0 volts because it's just going to sit there and act like a wire when nothing's changing. It has interesting behavior when current starts changing because a current flowing, changes in current give rise to magnetic fields, and that's how inductors store energy. They store energy in the form of magnetic fields. So let me write that also. They store their energy in the form of a magnetic field. Magnetic fields are also sometimes called B fields. I'm sure you know that. And so let me write the contrasts. Capacitors are obviously C in farads. And capacitors act like an open in a DC circuit. And they store energy in the form of a bless you.
Thank you.
Okay, so those are the similarities and differences. You can tell that there's obviously some inverse relationship between capacitors and inductors. The last thing I want to note is that we know the current through a capacitor is equal to C dVc dt, right? Well, we have a similar but obviously different equation for inductors, where the voltage across an inductor is equal to the inductance times the current, the rate of change of the current with respect to time. Okay, so those are both very important equations. They kind of give us an idea of how these components work. Okay. And then lastly, I talked about how energy in a capacitor is 1/2 CV squared, and energy in an inductor is 1/2 Li squared. Okay, so this is just a brief overview. Somebody asked me about, I think it was Hayden, asked me if inductors store charge the same way a capacitor does. And the answer is that they don't store charge. Basically what's happening is the current flowing through this coil gives rise to a magnetic field, and the energy that we have stored is being stored in the form of that magnetic field, where in the capacitor we're actually physically placing charges on the plates, which gives rise to an electric field, and that's how the energy is stored in the capacitor. Before I start, I don't think there's anything deeper to go into here. We're probably just going to jump right into RL circuits because they're very similar to RC circuits. So if you guys feel pretty confident with RC circuits, I don't think RL circuits will be all that crazy. But before I move on, does anybody have any questions about anything here or about inductors in general?
In simple words, you say what an inductor does, and how is it different from a capacitor? Because I understand capacitors, they store charge and they discharge.
Well, so basically a capacitor stores charge, and when it discharges, it can't discharge all of its charge instantaneously. Okay, it basically needs to take this exponential route of discharging or charging. Inductors store energy also, but their current can't change instantaneously because of this differential relationship. So if I were to say that this current can change instantly, I would assume that this voltage has to go to infinity, and that can't happen. So basically, an inductor is a wire. It's just literally a coiled up wire. Like I'm not making that up. Like if we look up what an inductor looks like, it's a coil. Typically has a magnet in the middle. I think I talked about this last time. And the magnet is there just because if we put a magnet, we can basically generate a bigger magnetic field and thus store more energy for the same amount of current flowing through the coil. And so some current will flow through this inductor, and it will have this magnetic field store energy. And then when we cut, the wire, or we stop the, sending the current, that current wants to keep flowing. It won't stop instantly. And so that's similar to how the capacitor wants to keep the voltage across it. The inductor wants to keep the current through it. And so when we look at the RL circuits, we're going to have to keep that in mind, because when we shut off the power supply, that current is going to want to keep flowing. It's not going to change instantly. So voltages in the circuit will change according to that current. Where in the capacitor circuit, currents were changing in the circuit according to that voltage across the capacitor. It's the opposite case for the inductors. Okay? So just so we can take a look, let's look at some inductors so you can see what I'm talking about.
Because we love to relate this to water, but would it be like filling up the top of a funnel with water and stop filling it, but the water's still going to slowly pour out the bottom?
Yeah. A lot of people like to use like a water balloon with like a pinhole in the bottom, and like you send water into the balloon and it starts to expand, and if you stop sending it in, it's still going to pour it all out the bottom until the end. And like people like to use that analogy. I want to show a couple. So there's an example. Here's a bunch of examples. This one looks good.
We talked about this physics, but that's like what they use in transformers, right? For second.
Yeah. So I think at the end of this unit of RL circuits, I might talk about transformers because they're easy to make in Spice and they're very useful. They're probably the main use for inductors. How many of you guys have heard of a transformer?
Like Megatron does.
Yeah, like Optimus.
They're heavy.
Yeah.
Mentioned it before in class.
Do you know what a transformer is, though? Like, does everybody know what they're for?
Yeah.
To step up and step down voltage.
For those of you who don't know, they're basically used to generate from some low voltage. They can be used to step it up to some higher AC voltage, and from a higher voltage, they can be used to step it down to some lower AC voltage. But the key, I keep saying AC, you can't use DC voltages because you need the changing current, right? Like I wrote down over here, voltage across the inductor is generated by a change in current. If there's no change in current, then the voltage across the inductor is zero and it just acts like a wire, right? Okay, so we got to see some inductors. We got to talk about them. I guess there's no more questions. Let me just real quick just show. I'll do a quick little DC circuit just to show that it behaves like a wire in a DC circuit. So I can throw that there. I'll put this here. I'll put that there, and then I'll put another inductor here.
So if you put DC voltage through a transformer, does it just act like a wire and do nothing?
Yep. It will do nothing. So basically, you have two coils. Like, take my two hands as the two coils. If you put an AC voltage on this one, it will induce a voltage on the other coil because of the magnetic fields that are literally like being induced by the current flowing. But if you just put a DC current through the coil, it's just going to act like a wire and it won't induce any voltage on the other coil. So let's just put some values in here. 1K, 1K. So this looks seemingly complicated, but because we know it's a DC circuit, it's very easy to look at. It's just the voltage divider, right? So we should expect to see V out should be 5 volts, right? Because both of these are just behaving like wires. So let me do a .op, run, and we see V out is 5, right? So the inductors don't do anything to this circuit. The currents are exactly what we expect. We've got 10 volts over 2K, so we've got 5 milliamps flowing. The inductors may as well not even be there. It literally may as well be as if I did this. Right? These are the exact same circuit. And so just to make that clear. So let's close this. Let's talk about, before I go into does anybody have any questions before I go to RL circuits? Okay. We have about 25 minutes. Your quiz is not on inductors, it's on the homework. It's on the homework from last time, so if everybody's comfortable with the homework from last time, you should be fine. Okay, so let's do an example of an RL circuit. So let's give me and also, so for capacitors we say charging or discharging, or we call the capacitor either charged or discharged. For coils or inductors, we typically say energized or de-energized. We don't say charged or discharged. All right. Got my R. Let's give it 1K, and then my inductor. Let's make it 1 milli. And let's say I want to start at 0 and pulse it up to 5. Alright, and then we'll call this V in, we'll call this V out. Okay? So, if I were going to analyze this circuit, I guess the best way to do it is to draw the waveforms. So let me just give myself some input. And I also want to look at the current through the inductor. So I'm going to call this V in. I'm going to call this one V out. And then I'm going to call this one the current through my inductor, okay? Alright. So, let's say that my input jumps from 0 to 5 after, I don't know, let's say 3 microseconds. And so that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my input does something like this. And then we'll just leave it on. We'll just do charging in this case, or energizing the coil. So initially when this is 0, I know that there's going to be no current flowing in the circuit because my inductor acts like a wire. So V out is also 0. It's just connected straight through a wire to ground, right? Okay. So when my pulse goes high, when it goes from 0 to 5, my input goes up to 5 volts. What's going to happen to my output is interesting. Okay, what did I say? I said that the inductor inductor's current cannot change instantaneously. Okay, how much current was flowing before the pulse went high? When it's at 0, how much current is flowing in the circuit? None, right? So the inductor is sitting at a current of 0 milliamps. Okay, and so at 3 microseconds. And V out is also 0 all that time. At 3 microseconds, when the source goes high, what does that current want to stay at? It wants to stay at 0. Okay? So if V out was initially 0, what does it have to jump to in order to keep 0 milliamps flowing in the circuit? Exactly. It has to jump up to 5. And the reason it has to jump up to 5, for anyone who's not following, is that if both sides of my resistor go to 5, I still have 0 current flowing through the resistor, right? So the inductor will force this voltage up to 5 because it doesn't want to change how much current's flowing through it. So you notice what's interesting about an inductor is we have 5 volts across it, but there's no current flowing through it. Because that's one of the interesting properties of an inductor. You're going to have to kind of keep Ohm's law out of your mind. Ohm's law doesn't apply to an ideal inductor because there will be voltage across the inductor and there will not be any current flowing through it. Okay, so that might seem counterintuitive, but this is not a resistor, it's an inductor. Okay, so we've got the current in the circuit is going to be controlled by Ohm's law and the resistor. So if this goes up to 5, to keep 0 milliamps flowing, I have to send the other side of the resistor to 5 also. Okay, and then V out will slowly bleed down to 0. I think I made the time constant here 1 microsecond. So this is another interesting thing. In RL circuits, tau is not R times L, it's L over R. Okay, so you're going to have to keep that in mind. For RC circuits, here, let's go back to the other page because I think this will be a useful note sheet for everybody. This is going to have all the good stuff on it. Let's write tau for capacitors is R times C, and tau for inductors is L over R. Okay, you're going to definitely remember that, because if you use L times R, you're not going to get the right answer. Okay, so let's go back to where I was. So if my tau is L over R, that means it's 1 milli over 1K, which basically gives me 1 microsecond, okay? And so that means that I should discharge, this was that 4, 5, 6, 7, 8. By 8 microseconds, I should be 99% of the way down back to 0 for V out. And note, right, my V out's final value is 0 because, again, what is it going to be? So here, okay, let me backtrack. For the capacitor circuit, I kept asking you, what is V out going to be basically in steady state when there's no more current flowing in the circuit? The reason I said that was because we know that in steady state, a capacitor basically acts like an open, so there will be no current flowing in the circuit. This is not the same for inductors. The inductor will basically, since in steady state it acts like a short, so this voltage V out is eventually going to go back down to 0, and I'm going to have 5 milliamps flowing through this resistor, right? So the question is, what is the circuit going to do when the inductor starts behaving like a short again? And obviously, if this is behaving like a short, V out is going to be 0. And so my inductor current, if my V out jumps to 5 and then bleeds down to 0, my inductor current starts at 0 and then charges up to the final current, which is going to be 5 milliamps in this case. Okay. I'm sure that there's questions. So does anybody have any questions about this? Yes.
Just to clarify again, that means that there's no voltage difference on either side of the inductor, but it still has a current running through it.
Exactly. So when there was 5 volts across it, there was no current flowing through it. And when there's no voltage across it, there is a current flowing through it. That might not always be the case, but that's very counterintuitive based on what we've learned so far. But you're correct that at steady state, Vm will be 5, V out will be 0, which means there will be no voltage across the inductor, but there will be 5 milliamps flowing through the inductor. Okay? Let's go do this in SPICE.
What is a real-world application of an inductor? What do you
All the funnest
use
stuff.
them for?
They're used in, so a lot of inductors and capacitors are used in filters. They have what's called frequency response characteristics. They behave at different frequencies differently. I talked a little bit last time about that, I think, when I was talking about impedance. And basically, inductors and capacitors pass through different frequencies. They'll let certain frequency signals through, and they'll block other frequencies because they act like opens at certain frequencies and act like shorts at certain frequencies. So if it acts like a short at a certain frequency, it's going to let that signal through, right, like a wire. But if it's acting like an open, it's not going to let that signal through. So inductors and capacitors both are often used in filters to filter out certain frequencies. And if we have time at the end of the course, I can go over frequency response, but this is stuff that you'll go over in 221.
Inductors are also the basis for electromagnets, which makes them fun.
Yeah, so you can Yeah, you can make an electromagnet using an inductor. Transformers are made using inductors. There are all kinds of. What's that?
We were talking about that in physics yesterday.
Railguns?
Using a disposable,
What's a railgun?
A disposable
electro-
camera
it's-
to shoot stuff.
It's an
with a
electromagnetic.
You
magnetic.
took a straw
Accelerate
and wrapped a bunch
particle
of coils around it and sent a current through it. You could basically get it to shoot a projectile.
Oh, geez. I think Electro Boom has a video like that. It sounds like something he'd do.
It's just basically putting a bunch of electromagnets and then firing them all off at the same time to get a piece of metal to move.
I see. Yeah, I think I saw something like that on YouTube.
It's fun.
The weapon that'll bring back battleships.
All right.
Let's go.
All right, so I got my circuit here going from 0 to 5 at 3 micro. That's exactly what I did here, right? And so we should see this exact behavior. V out should shoot up to 5 and then bleed down, and my current should slowly rise up to 5 milliamps, because in steady state, right, in steady state, V out is going to be 0 because the inductor is going to act like a wire, and if there's 0 at V out and 5 at V in, I'm going to have 5 milliamps flowing through the resistor, and this is one single loop, so it will be 5 milliamps flowing through the inductor as well. I'm going to run a transient for 10 micro, and I'm going to split my plots. You know what, let's throw the plots on the other side of the screen. Ugh. I wish that there was like a better way to do this. Like they have a tile horizontally button, but they don't have a tile vertically button, or vice versa. They have a tile vertically, not a horizontally. Okay, so I wanted to plot V in, obviously. I wanted to plot V out. Does exactly what we said. And I wanted to plot, hang on. I want to do it in the same order I did on my page. And I want to plot the current through the inductor. Okay? So this is exactly what the kind of behavior that we expected. I want to note that the Fife equation is going to be your best friend because it works for voltages and currents in capacitors and inductors. Okay? So I'm not going to rederive it for all 4 of those cases, but in general, if you want to know the behavior of these circuits, basically for voltage, whether it's an inductor or a capacitor, you can use V of t equals V final plus V initial minus V final, e to the minus t over tau. This is why we use tau, by the way, because this equation works for either tau. You just have to know which tau you're using. And for current, it's going to be the current at any given time is equal to the final current, right, plus the initial current minus the final current, e to the minus t over tau. So if you memorize this equation, you can use it for every single one of these circuits over and over and over again, as long as you know, and this is where the actual challenging part comes in, is knowing what are your initial and your final values. You have to understand how the capacitors and the inductors work so that you can determine, okay, V out is eventually going to go to 0, right? Because it's connected to an inductor, and the inductor is going to act like a short when nothing's happening, okay? So V out going to 0, and you have to know that V out is going to jump to 5 when this pulse is high, because you have to know that the inductor doesn't want to change the current flowing through it. So if you want to write this equation, that's great. You know you use Fife, but if you don't know VF and VI, then you're not going to get anywhere, okay? So this particular one would be 5, right, plus, oh, sorry, it's final value 0, its initial value is 5, so it's going to be 5 e to the minus t minus 3 microseconds over tau, which in this case is just 1 microsecond. Okay? And then this equation is for the current, right? It's going to be, its final value is 5, its initial value is 0, so this is going to be 5 times 1 minus e to the minus t minus 3 microseconds over 1 microsecond, and that's going to have units of milliamps, and this is going to have units of volts. Everybody see that? Any questions? No questions about this?
Where did we get the 30 microseconds that we're subtracting from tau?
This initial like shift where nothing's happening. Okay, so basically, it's like, you know, in I explained this to somebody in my office. Let's say I have the function y equals x, right? If I want to shift it over to here, let's say I shift it by 3 units. Now I'm plotting y equals x minus 3, right? So the same thing's the case here. The general case of these charging and discharging equations, it's assuming that you're starting charging at 0, or it's assuming that you're starting discharging at 0. So if you want to shift it, you have to subtract out that shift from the variable.
So you just offset it based on where you start.
Exactly. That's literally it. So if this pulse went high at 30 microseconds, then you'd subtract out 30 microseconds,
Okay.
right? Because then you're going to plug in 31, and that 31 minus 30 is going to give you that 1 microsecond that you're actually interested in, that 1 microsecond after the switching began, right? Does anybody else have any questions about this? All right. Let me go look at your homework and see if there's anything I didn't cover. So sketch the waveforms for V in, V out, and I in each of the circuits. Verify that waveforms are correct. Okay, you can do those now. This should be easy. Okay, so for this problem, note that it's the same thing, except you know how in the capacitors I can either use a pulse source or I can use a battery with a switch. It's the same thing, right? Initially, this switch is open. The switch is going to close. It's going to act the same as the pulse would. And then I tell you to rerun the simulation for this. So notice that the transient simulation is 35 micro here. I tell you to rerun the simulation, but change the transient time to 40 microseconds. Okay? And I ask you to describe what happens. So something crazy is going to happen. And it's up to you to determine what that is and why it happens. And then if you have questions, obviously ask me. Not right now. I want you to think about it. And then I'm going to ask you to devise a plan to, I said discharge the inductor, but that's not technically correct. I would say de-energize would be a better word. Basically, you need to provide, it's very similar to the capacitor one, right? I gave you guys that one where the capacitor didn't discharge. This is very similar to that. But you're going to see something crazy is going to happen in LT Spice, so talk about it, and I think you're well equipped to do this homework. I guess, yes.
So for the last question, did you want us to run it like with the, you know how he says you can add components?
Please do. Please do.
Oh yeah. Did you want us to run it when we add the components or before?
I want you to run this circuit for problem 2 exactly how it is with this transient. And then for problem 3, I want you to run this exact same circuit with 40 microseconds. Note what happens, make some changes, and try to fix it, and then run it again once you've tried to fix it.
Okay.
Okay?
The question doesn't ask us to show anything in Spice though, so it's just a block of text, right? Like we'll just be writing out our findings.
Yeah, you don't need to show it. I mean, I guess I would have liked to have asked you to show what you did, right? If you just write what you did, I can't really. There's nothing there really.
I'll draw a little picture of the smiley face.
I mean, I can't say verify with LT Spice because people could have different solutions to this problem.
Right.
So I want you to show me what you did. Like, if you have a solution that's going to fix the problem, obviously I want to see that schematic, and I want to see the plot, and I want you to describe how you fix the problem.
Why don't you just throw in a line that says show solve schematic or something?
Do I have to?
You don't have to.
Oh, it's homework 15.
I'm just saying.
All right, I guess I'm going to do it.
Just saying.
But then what if somebody already started it?
Such a good.
That's true.
Don't forget to change it to de-energize as well.
All right. Any other things I screwed up?
Just start a list.
Where is it?
Honey-do list for the homework. Please show your findings using
clear LT spice plots. Good? I'm leaving it. All right. Now I have to upload it. What a waste of time.
You're gonna get through this.
I know, but this is wasting precious time. You guys could be asking me way more important questions than watching me post the homework.
I have a mildly important question. How does an electric engineer not know what a railgun is?
I don't know.
I just legitimately like that's like the coolest thing about like electrical engineering is magnetizing things to move fast.
I know, but I don't know much about electromagnetics. I had to study these inductors before I taught them to you guys.
Oh, okay.
All right, let's see. Did I fix it? Update. Yay. Please show your findings using clear LT spice plots. All right, and I changed it to de-energize.
Is that another typo?
Where? If it was, I wasn't going to fix it. Okay, one more thing I want to do before I give you the quiz is I want to talk about if the inductor and the capacitor were flipped. That's probably what I'm going to give you on the next homework, but just so we can get another look at how this stuff's working. I'm not going to plot everything. You know what? Let's just do it in Spice. That'll be better. And we'll talk about it. So let's flip the inductor and the resistor. They're the same size, so you won't have to deal with that. Okay, so now what's going to happen? Vn's going to go 0 to 5, right? And I want to keep 0 current flowing through my inductor. So what do we think is going to happen to V out?
I would assume it's go to 5 as well.
Well, if it went to 5, then I'd have a current flowing through my resistor.
Zero, right?
It should just stay at 0. It should just stay at 0 because if Vn goes to 5, again, and a voltage across the inductor doesn't matter to us. A voltage across the resistor matters because we don't want to change the current. So V out should stay at 0, right? So let's run this. And it stays at 0 when this pulses, and then the current and the voltage basically go up together because V out's going from 0 to 5, so my current goes up proportionally, right? That's basically, we're looking at Ohm's law right there, right? It's basically V is equal to I times R. If I took this I and multiplied it by 1K, I get this waveform for the voltage, right?
And that is the inverse of like a capacitor. Since if you had a capacitor with a resistor in the front, then it looks like that.
Yeah, exactly. Okay, I guess I'll give everybody the quiz a couple minutes early. Any other questions?